we trying to talk about? Not trying to talk about, learn. Scientific notation. Okay, so like I said, in scientific notation, so here, you look here. Can you see my arrow thing, cursor? Yes? Okay, good. So this here is the whole scientific notation. Okay, scientific notation, you have your conventional, so the standard. And like if you change the powers here, you can write this in many different scientific notations. But the conventional, the standard way of scientific notation is that your base number, which is the one before the times, should be a number between 1 and 10. Okay, so that's your conventional. So 1 to 9, okay, that's your standard convention. And then times 10 to the whatever. So here our example is 2,400. When you write this, they don't put the decimal point, but the decimal point should be here, right? Are you seeing it? 2,400 dot. Okay, so when it's greater than 10, then your power is going to be positive. So you count from your dot, which would be here, and you would count 1, 2, 3. It's 3 away. That's why you have your power 3. And then you'll have 2.4. That's your coefficient, or some would call it a base number. So 2.4 times 10 to the third power. And this is another way to write 2,400. Okay. This 2,400 also can be 24 times 10 to the 2, right? That is also a scientific notation. 24 times 10 to the 2. Yes? Right? But then, is that a standard scientific notation? 24 times 10 to the 2. Why not? Why is 24 times 10 to the 2 not a standard scientific notation? Because your base number, your coefficient is not between 1 and 10. 24 is higher than 10. Okay, so that is not your standard scientific notation. So if in a question I ask you to write the number in a standard conventional scientific notation, the coefficient should be between 1 and 10. Okay? Okay. So here is how it's put, 3 places. You have 3. So 2.4 times 10 to the 3. Okay, here, what do you have here? That's your decimal place. 1, 2, 3, 4. You will know that is a very small number when your exponent is to the negative. So 1, 2, 3, 4, 8.6 times 10 to the minus 4. Okay. So this is how you write scientific notations. Okay, we'll have more examples. So positive number greater than 1. Okay, 10 to the 0 is 1. And then negative exponent is less than 1. So the 10 to the 3 means 10 times 10 times 10. 1 times 10 to the 3. 0 is 10 to the 0 is 1. And then 10 to the 4 is 10 times 10 times 10. That's why it's based on the multiples of 10. Okay, This is your base of 10. Well, we have to do the background. You'll have to write numbers big and small. We talk about atoms. Atoms are very small. Or later on, we'll talk about Avogadro's number. What is Avogadro's number? That's a really big number. This is basic math. 5th grade does this? Do 5th graders do scientific notation? I have to ask my kid. Anyway, so multiples of 10, 1 over 10, 0.1, 1 over 100, 10 to the minus 2. Okay, if you have a negative number, this is our rules of exponents too. Okay, so this is your review. 10 to the minus 3, 1 over 1,000. So to put it in perspective, why we write scientific notation, the volume of gasoline used in the United States is, what is this? A big number in liters. Okay, thousands, millions, what, billions, trillion, the diameter of the earth, the average volume of blood pumped in one day, 8,500 liters, time for light to travel from sun to the earth, mass of a typical human, mass of the stirrup bone in ear is really light. The diameter of a virus is really small. The mass of a bacterium. So these are all numbers that we don't have to write all the zeros if we know how to write the scientific notation. And this is another slide that will help you write it. So this is the decimal place. You count. And then you put your base number between 1 and 10. Okay, here, 5.63. Yeah, this slide I'm gonna post after lecture. All the lecture slides are gonna be posted on Blackboard, so you can review the slides, okay? Here, you'll know this will have a negative exponent because it's less than 1. So 1, 2, 3, 4, 5, 6. Okay. And then we'll do examples, and the homework also will have questions on how to write scientific notation. So this is just how we write numbers, data, which is part of what we gather during experiments. Okay. Letter A. What is this in the correct standard scientific notation? 64,000. Okay. Where is my, oh, it's on participant, the raise hand. Brian, okay. Okay, you have it on the chat board already. Let's see if your answers are correct. So you have your decimal place here. 1, 2, 3, 4. 6.4 times 10 to the 4th plus 4. Everyone is following. Everyone knows what's going on. Yes or no? Okay. Good. Letter B. Okay, this is less than 1. So then 1, 2. 2.1 times 10 to the minus 2. Okay. Questions? No? Moving on. Okay. Measurements, data. So here we have the standard system of measurements. We have the British system. We have the metric system. Okay. And like I said, when you do science, you have to communicate. Okay. When you just see a number, that number doesn't mean anything unless it has a unit, because you don't know what it's measuring. Okay, so you have to have a unit so you know what it's referring to. So here, these are data, and this has units. AM, you know that means time, okay? Or how many in Celsius or in Fahrenheit. In here, you have mass in kilograms. That's the metric system, or the British system in pounds. You have what is this? M. What is this unit of? Meters is a unit of what? Distance or length. Okay. So mass, length, more length. Okay. So like I said, in experiments, you get data. You have quantitative, you have qualitative. Quantitative deals with numbers. Qualitative deals with what? Quantitative, quanta, deals with numbers, numerical values. Qualitative, what do you think is qualitative data?
Studies the properties of things.
Okay, what kind of properties?
Like if something is, I don't know. I mean, you can measure efficiency, I guess, with numbers. Like, I don't know, like how people feel about taking a product is one.
Okay. So usually, like when you have food analysis, you have, you know, before they let out a food product, they have people who come in, a sensory project, and then they have to write down properties that they like about it, other than the numbers. So Andy says here, appearance, physical characteristics. So what would be a property? How would it appear to you? What factor would you describe as a physical appearance? Okay, here, look at the picture. Let's look at the picture here. What would be qualitative data that you can write down based on the picture of this couple walking down the road? What would be? So here we have this quantitative data. So you have and the temperature of each. What would be the qualitative? L, quali. What would you say? The man is taller. Well, taller is length. So I guess that could just, well, you can say taller than this much, then it would be quanti. No, I'm talking about the couple. What is the number one thing that you would like? That's not nice. Okay, so red shirt, blue shirt. This is a blue shirt. Okay, that would be a qualitative data. Okay, color. So these are all, it's important. Okay, she has brown hair, she has wavy hair, and then the wavy, you can actually figure out how much curly, loose curl, tight curl, that is quantitative measurement. Okay, so both types of data. But the next slides, we're going to use the quantitative data. Okay, so here, you have different things that comes out to you from a slide. Where is a skateboard? All right, that one. Hey, you know the skateboard Olympic champions, they're really young, right? You go to a skateboard park, ooh, it's really scary. I don't know how people can go to like half pipe and stay standing when they come down. But anyway, the Olympics, they had very athletic people there. Okay, so measurements. We talked about writing numbers big and small with scientific notation. We also talk about measurements in the metric unit, in the British units, and we talk about here, the next slide, how the units work when we collect data, okay? You look at these two pictures, if you don't know anything about it, you would say that these hexagons are the same size. But on the bottom of the picture, it shows that, what does it show? The actual, what? Sizes of these hexagons. So here, what do we have here? This is an atom with 6 sides, hexaatom, and this is a beehive. So which one is a bigger object, A or B? The beehive is bigger than your hexaatom system, right? Why? How did you come up to that conclusion? Why would you say a beehive is bigger than a hexaatom? Okay, so you have, what did you say here? The negative power is smaller. Very good. Do you know what that means? The negative power is smaller? The exponent, yes. So 10 to the minus 3, meaning what? You're 3 away from your decimal point versus 10 to the minus 10, you're 10 away. So if you write it down, can you write it down? How would you write it down? Who can write it down? In letter A, okay, Michael's writing it down. The next one is, so A, write down, who's writing down? Okay, write on the chat board A, what is it in a conventional number, like a regular number? A is, no, Timothy, let's see, Timothy, are we counting? Can everyone see the chat board on their screens? Yes, okay, don't pull it up. It's gonna go away. Did Timothy write the letter A? Is it Timothy or Marbelli? Well, you have so many there. Okay. So Michael has the last one. Let's focus on what Michael wrote here. Is 5 times 10 to the minus 3 the correct number? 1, yes. Okay, and the, so if you look at those numbers, that is what those mean. Okay, 10 to the minus 10, 10 to the minus 3, right? So a beehive is larger. It is a more positive, meaning a smaller exponent than the 10 to the minus 10. Okay, so now to the question here. How many atoms? So each intersection here is an atom. So it's a hexa, 6 atom. So how many of this can fit into a beehive? How many do you think? How will you do this? How in one beehive, how many of these atoms fit? So what do you do? This is segueing to conversion factors. Let me see. Divide, very good. So you do, you divide 5 times 10 to the minus 3. How do I, can I check? Okay. So what do you do? 2? Only 2? 5 times 10 to the minus 3 divided by 3 times 10 to the minus 10. So how many do you have? Okay, in scientific notation, what would that be in scientific notation? That's a big number. You can have so many hexaatoms in one beehive. How many? Calculator, here, calculator. 5 times 10 to the minus 3 divided by. Are you following, everyone? I'm just like yakking here and no one actually knows what's going on. So in scientific notation, 1.67 times, okay, 10 to the 9. Is that right? 1, 2, 3, 4, 5, 6, 7. No, I only have 7. It's from the decimal place. You go from the decimal place. Are you following? Yes, no, you have to speak up. So the number of hexaatoms that can fit into a beehive, yes, 1.6 times 7, 1.6 times 10 to the 7th power. Okay? In scientific notation. Questions? You need to speak up.
I got preoccupied by something in my house real quick. So where did the 1.6 come from? I'm sorry, I just came back.
Where did the 1.6 times 10 to the 7 come from? How did you do it? Who wants to answer? This is like a lecture class. Focus on what's here. So Christopher wrote, it's 5 times 10 to the minus 3 divided by what is the size of the hexaatom? So it's 1.67, but do not forget your exponent.
Yeah.
So it's going to be 1.67 times 10 to the 7. So more than a million, right? More than a million hexaatoms can fit into a beehive. That's how you can think. A beehive is really small already. And one beehive can fit more than a million hexaatoms. So that means your atoms are really tiny. That's why we're doing all this scientific notation. Everyone is on the same page. We're moving along.
Yeah, I got it.
Yes? Good. Okay. Okay. No question. So, metric system, British system, and then we have the system used by the scientific community, and this is what is used by the scientific community. So if we talk about number of entities, meaning this is the collective term, motyam is what? No, what does that no mean? What does no mean? Oh, no question? Oh, okay. Okay, I didn't know where the no came from. Okay, so like I said, you have units, you have the metric, you have your British units, and here, these are the physical quantities. So when you talk about number of entities, like for example, the hexaatom, 6 atoms, but then you would say one beehive would hold 1.67 times 10 to the 7, more than a million atoms. So instead of writing all of those zeros for the many millions of atoms, later on we'll talk about moles because atoms are really tiny. When we talk about length, the distance between two things, we use meters. We talk about mass, we use grams. We talk about volume, we use liters. We talk about temperature, we use degrees Celsius. Time in seconds, information in bytes. So you have your gigabytes. What's the biggest storage, external storage that you can get now? What is sold? There's a terabyte. Is there one more than a terabyte? Huh? Do you know of any storage external hard drive that has a higher storage? What is this term? That can hold. Okay, so 4 terabytes. It's a lot of info. Okay, so like I said, measurements deal with data. Data here is quantitative. Okay, and then yottabytes There's a yottabyte? I haven't heard of a yotta. I think that's made up. Is that really a
Nah, I've heard my friends tell me about that actually.
there's a Google, Gogol. That's the biggest prefix, which will come later on.
Really?
Yeah, it's not,
Makes sense. That's probably all the search results you could probably get on YouTube ever.
but
It's huge.
scientific notation, petabyte. Are you like computer science people here? What are your majors?
I'll put it in the chat.
Computer science.
Okay, so really there's a petabyte. Music, okay. Mathematics, psychology, biology, psychology, undecided, economics. Oh, we have a mix here. Well, you can apply chemistry to anything. Textiles. Petabyte is 1 terabyte. Is 1,000 terabytes. Peta. I don't see peta here. I guess we have to update here. You have to like have more and more. Well, you have to have every zero you have, then you'll have a symbol or a letter. Is a prefix. Where can you learn quantum mechanics? That's higher chem. It's a physical chem. If you go into chemistry, you can do quantum mechanics, or you can go to physics, you can go to quantum mechanics. They look at it from different sides. Okay. You want to make an Ant-Man? The realm of, did you see the science news? You see the news that Einstein was proven right. He has a theory that was proven right with a black hole. I didn't read. Like he proposed this theory about time from I don't know how many years ago. And now they have the sophisticated instruments that are able to like look at these black holes and then say, yep, time is whatever Einstein said. Okay, there's a recommendation here, Interstellar. Okay, where were we? Oh, we're looking at numbers, big and small. Okay, so we do scientific notation. We also have prefixes. So here, the examples, tera. What's tera? It does not, it means something, tera. Okay, there's recommendations here if you want to list it down about science stuff. But back to our lecture. Or when you look at sci-fi movies, you can look at it analytical. Does that really make sense? Okay, and then you can think about it. But anyway, back to our slide here. So scientific notation, we write it so we don't have to do all the zeros, big and small. Prefixes are also, they also function the same way. So instead of writing all the zeros, so we have a base unit, okay? What are the units that we discussed in the previous slide? What were the quantities that we can measure? Units, that would be the base unit here. That would have the 1. Do you remember? Let's take 1 unit, for example. A unit of information storage. What was that unit? Byte, okay? So 1 byte, then we can say 1,000 bytes. But instead of saying 1,000 bytes, do we have it here? We can say what? Using a prefix. Use this table here. 1 byte, 1,000 byte is equivalent to a kilobyte. Very good. You know what's going on here? A nibble? Is that, what is a nibble in byte terms? Is a nibble in byte terms?
I forgot who it was that developed the units.
Yeah.
But as a joke, he said like the smallest unit would be called a nibble. I heard this like when I was in middle school. So I could be wrong, but I mean, it made me laugh when I heard it.
Okay, but this is also, look it up. Let's see, a byte. Oh, okay, at least Kyle got the reference because a byte can be a nibble. They just changed the I. I didn't even think of that connection. Maybe if you have another kind of computer storage that instead of a byte, you use a nibble. Anyway, what were we talking about? Scientific notation, big and small numbers, you use exponents. Prefixes, you use the same thing. Instead of putting a lot of zeros. No, I'm going to give you a chart. But you'll have to know how to use the chart to convert from one prefix to the next. Like 100 centimeters is how many meters? I'll give you the chart later on. So instead of writing the 2 zeros, you use something else. Okay, where's my next chart? You see my chart on the bottom?
Yeah.
This is what you're gonna, well, when you do the test, okay, you use this one. You can use this one. So your base unit, for example, here is your centimeter. So 1 over what? Let's go to the next slide with an example. This is not really making sense to me. Okay, let me just, is everybody not, well, are you following what's going on with the slides? Yes. We need the feedback on the way so that we'll, I know how it's going. Yes, no. Okay. Yes, that's good. Okay, so these are the physical quantities. And, okay, that's good to know. You can always speak up too, instead of just chatting, and then I'll have to follow the chat. So 1,000 millimeters equals 1 m, right? This is what you see. That is what you call an equivalency. You use this to go from one unit to the next. So the equal sign can be written as over. 1,000 millimeters is 1 meter, or it can be written as 1 millimeter is 1,000 meters. So if you want to say 2 meters is how many millimeters? Okay, 2 meters is how many millimeters? You would use which factor? This one or this one? How would you go? We are going to do conversion factors now.
Second one.
Who wants
One, right?
the right? This one, 1 millimeter equals over 1,000 millimeters would give you.
Yes.
Okay, what did I say? What did I say? I'll write it down. 2 meters is how many millimeters? That's what I said, right? Yes. Let me stop share.
Yes.
Okay. Let's talk about units like numbers. Units like numbers go with whatever operation like numbers. What does that mean? If you say, I need to go to a blackboard. My old blackboard didn't work. I'm gonna use this blackboard. Let me use this blackboard. Okay. Stop share. Wait, sorry. Let me use a blackboard. Do you see my board on your screen? Yes?
Yes. Yes.
Mm, where is the thing? I had it right. Okay. What was it? 1,000 meters over 1 meter. Can you see what I'm writing? Versus 1 meter over 1,000 millimeters. Can you see what I'm writing?
Yes.
Yes.
I say 2 meters
Yes.
3 millimeters. And I'm saying which one should I use, A or B? This is dimensional analysis. You say B. Okay, so you plot it out. So 2 millimeters times 1 meter over 1,000 meters.
You want to try?
What would your units be? Would you have the correct unit?
Yes.
Meter, like I said, units are like numbers. If this is a multiplication sign, then you would also have a multiplication happening with your units. So then here, meter times meter is what? It's gonna be what?
Meter square?
Yeah, it's gonna be meter squared over millimeter. You're not converting it from one unit to the next, right?
Yes.
So then that is not how you convert meters to millimeters. It's gonna have to be A then. You understand what I'm saying? Units are like numbers. So if you use A, eraser. If you use A, how do you use A then? So 2 meters times 1,000 millimeter over 1 meter. What would be your units?
Millimeter.
You would have meter times millimeter over meter. And this one, meter divided meter is 1. So you will have a new unit of millimeter. Are you following?
Yes.
Yes.
That is dimensional analysis.
Yes.
So that is what you think about when you're converting from one unit to the new unit, okay? Think of the units as numbers. If they don't cancel out, then you're doing the wrong conversion factor. Yeah, okay. That's why you think like you can just look up everything. But you have to know the basics, at least know where it comes from. Okay. You understand that's conventional analysis. Okay, where were we? I was telling you how to do conventional analysis. Okay, and so here, method that uses conversion factors to convert from unit to another. Okay, that's not a good example. This is what I'm telling you about. Units are like numbers. cm times cm, you'll get cm squared. Are you seeing the slide that I have the units are like numbers?
Yes.
Good.
Yes.
cm plus cm, that's why they said you cannot add apples plus tomatoes, then you'll have, your result is still 6 apples plus 6 tomatoes. You need to convert tomatoes to apples, which you cannot do. So you need to add of the same kind, same unit. cm divided by cm is 1, like 2 over 2 is 1. Okay? Okay. So this is These are your conversion factors. These are equivalencies coming from measurements. So 1 meter is 100 cm. 1 meter is 39.4 inches. 1 meter is 1.09 yards. Okay, you have from metric to metric. You have from metric to the British unit. Okay, so, and then you write it down as your conversion factor over, and what you put up is that same thing here. This one you use cm over inch or inch over cm, depending on which way you want to go. Which one would be your old unit? Which one would be your new unit? Okay, that is how you are going to work. And this is dimensional analysis. You use the dimension. What's the dimension? The unit to guide you in the conversion. So here, old unit, they should be opposite, because this is like old unit over 1 times new unit. Old unit divided by old unit equals new unit. Okay. Okay. And this is what I said. We can go from metric to British. So ml to cm cubed or cc, these are all equivalent. Milliliter. This is volume. So that's why, what is a volume? Formula for volume. Volume for a cube. Who remembers geometry? Is there a what's the volume?
Length times width times.
Length times width times height. So that's why this unit of volume, milliliter, also is cubic centimeter, because centimeter times centimeter times centimeter is cm cubed, or cc, cubic centimeter. That's why milliliter is cc is cm cubed. You can see this, like, where can you usually see volumes in terms of cc? Where do you see these things? Any medical person here going into a medical field? If you look at syringes, they have cc's, ml, okay? That's the same thing. So 1,000 ml, what's the base unit? 1,000 ml is 1 liter, okay? 1,000 ml is 1,000 cm cubed, is 1,000 cc, okay? This is your 1 liter. This is a graduated cylinder. 946 ml also is 1 quart. See a quart, if you buy soup, 1 quart of soup, it's not really a liter, close to 1 liter. Okay, so these are units which we use. Another unit, temperature. Today is, what's the temperature outside? What's the temperature outside? Is it in the 80s or 100? $90 degrees? Okay, 90 degrees Celsius. Is it 90 degrees Celsius? I told you. Fahrenheit, very good. No unit doesn't make sense. Well, I guess because you live in the US. It's, you say, oh my gosh, it's really humid. Okay, so 90 Fahrenheit. If you have these formulas here, what is 90 Fahrenheit in Celsius? How would you do that?
You would just substitute. Once you just put 90 in there, that equation, that would spit it up.
So the top one, right?
Yeah.
90 minus 32 times 5 divided by 9. Is it 32?
Yeah.
Okay. 90, let's see, 90 minus 32 times 5 divided by 9 is 32.22. Or if it's, what about the temperature of room temp? Room temp is usually, by convention, 25 degrees Celsius. So what is 25 degrees Celsius in Fahrenheit? What is 25 degrees Celsius in Fahrenheit? You know, 9 over 5 is 1.8. So that's easy. 1.8 times 25 plus 32. What is 25? What is room temp in Fahrenheit? So 1.8 times 25 plus 32 is 77 Fahrenheit. Does everyone follow? You know how to use these formulas?
Yeah.
Temperature is straightforward. You use this with so 1.8 C plus 32, and you have this. Okay. Okay, so this is just another dimensional analysis from grams to kilograms. Okay, like I said, what you look for is which units are the ones you want to convert, and they have to be on the opposite side of your fraction bar. You know what I'm saying? Opposite side. Because you want to cancel it out. So it's gram over gram. Okay. So this is what you try to do for dimensional analysis. Okay, and this is another picture of the different conversion factors. So 1 kilogram is 1,000 grams. You will always get the conversion factors. Like if you need it, I'll put out the conversion factors. All SI, Systems International. Remember how I said the scientists need to talk to each other? So they have a uniform unit that is accepted in the scientific community, and they use the SI units. So the SI units is from the French Systems International. Okay, that's International, NALE, and this is what is used. So that's the slide that you have here. Okay, the one that has the base units. Maybe it's coming to the other side. Where is it? Oh, sorry. Okay. Where is the Systems Internet? Okay, these are the base units. Can you see it? Michael, who asked about the SI units? Because you have different metric units, but these are the units that are used when you talk about these different quantities. Then the units, these are the base units for each quantity. Does that make sense? Okay. Oh, I have a poll. I have a poll. Okay, another poll. Where's my poll? Okay, let's see if you know. Well, we'll do the poll first and get the answers for the thing. Abbreviation for the prefix mega. Which one? Mega millions. So if you put mega millions in scientific notation, what would be the scientific notations? Mega is what? Million is what? What is mega? Is megameter larger than a meter? Yes? What do you think? At 1 minute mark, megameter is bigger than a meter, yes. Okay, 3, 2, 1. So which one is it? What is mega? It's gonna be big M, okay? Mega is big M right here. Mega is big M. You see it? So that's mega. Okay. Fill in the blanks with the correct prefix. 1,000 meter is which one? What is A? Very good. Okay, this is 10 to the 3 meters. So whatever your base is, that's gonna be on your bottom. So 1 times 10 to the 3 meter is 1 kilometer. Okay. 1 times 10 to the minus 1 meter is 1 decimeter. 1 times 10 to the minus 2 meter is 1 centimeter. Are you following? Okay, what about letter B? What's letter B? 10 to the minus 3 grams is your base unit. So where is the 10 to the minus 3 here? Right here. So just looking at this table, 10 to the minus 3 grams is 1 milligram. Very good. So small m is milli, big M is mega. And right here, okay, this one then, this is not as straightforward. 0.01 meter. Which one is this? What is that in? You need to put it in scientific notation. 0.01 is what? 10 to the minus what? Uh, 10 to the minus 2. Very good. Remember? 1, 2. 10 to the minus 2. So it's going to be centimeter. Are you following?
Yes.
See, this
Yes.
is less than 1. So you would know your scientific notation here, the exponent is going to be less than 1. How many? 1, 2. So 1 times 10 to the minus 2. Where's 10 to the minus 2? Here. Okay, so 1 times 10 to the minus 2 meter is 1 centimeter. Here, what is the scientific notation here? This is greater than 1 greater than 10. So 1 times 10 to the 3. 10 to the 3 meter is a kilometer. Okay? Questions? Any clarification, question on conversion factor? Milligram, small m. Small m is always milli. So how many grams is 1,000 milligrams? Does that answer your question? That's correct. 1 gram. That's correct, Lauren. 1,000 milligrams is 1 gram. Or 1 times 10 to the minus 3 gram is 1 milligram. Does it answer your question, Michael? Well, that is not, it's not in this one. I won't ask you that question. There's no prefix for it. Well, maybe there's a prefix for it, but it's not used much. Hey, who said peta? Here, we see peta, it's 10 to the 15. They have 1 petabyte memory storage. Yes? Who was it who put on the chat petabyte? Did someone put a petabyte? I think I remember a peta. Anyway, it's here, 10 to the 15. Okay. We did quantitative, qualitative. What do we have here?
If you ever want to ruin hedgehogs for yourself, just look at what a hedgehog looks like without their fur. You ever seen that before?
No.
A hedgehog without their fur, they don't look very pretty.
We saw a groundhog out in the east when we went out to the we went to the
See, look in the chat, look in the chat. I ruined it for him.
So a hedgehog. So these are the things that hibernate. So this is your conversion factors. So here we did this. This is going to be given to you. So convert the body temperature of a hibernating hedgehog. So they hibernate. Is 26.8 freezing temp or no? What's freezing temperatures?
I forgot.
What is freezing temperatures? Below 0 Celsius or 32 Fahrenheit. Very good. So they can survive. Yeah, below 0. Which one is smaller, 32 or 26.8? So see, okay, always I tell my students, you don't just use the formula and not put it in your head if your answer is correct or not. Well, here you should know that freezing temp is 32, right? Do you know that freezing temp is 32 Fahrenheit? What is boiling temp in Fahrenheit? Boiling temp is what? Boiling temp, when your water boils, the temperature of the boiling water is very
It's at
good.
100 Fahrenheit.
No, not
Oh.
Fahrenheit. What is 100 Fahrenheit in Celsius?
Pretty hot.
No, it's low. You go out, you say today is 100-degree weather. If it was 100-degree weather, all the water around you should be changing to water vapor. That's what you think. Boiling point of water in Fahrenheit is what? Use the formula here. Did you use a formula? 200, no, it's 212 actually. So, okay, let's use 100 degrees Celsius. This is correct. Who did 100 degrees Celsius? Kyle? Did you say boiling point is 100 degrees Celsius? So if it's 100 degrees Celsius, then you change this into, okay, so what would it be now? 100 degrees Celsius in Fahrenheit. You do not go out when it's 100 Fahrenheit. You expect that you're going to be boiled off. Well, not you, but the water is around you. So 9/5 or 1.8 times 100 plus 32 is 212 Fahrenheit. That's the boiling point of water in Fahrenheit, which is 100 degrees Celsius. And that's what I said. When you do conversions, you look at the numbers. Here, it says this is 26.8 Fahrenheit. That's when they hibernate, okay? And you are asked to convert this in what? Celsius. Well, I think it's common knowledge that freezing temp in Celsius is 0 degrees Celsius. Am I correct? Everyone should know that 0 degrees Celsius is freezing point. Okay. So, concept check. Is your answer correct? conceptually. That's what I try to tell students. If this is 26.8, living in a temperate region, using the Fahrenheit scale, we know freezing temps is 32. If you go through with this and you get in a number that's negative, okay, it should tell you that your answer is correct because 0 degrees Celsius is freezing temp. Then this is smaller than 32 Fahrenheit. Then this should be negative in value. Do you follow? Yes?
Yes.
Okay, that is concept check. It is not enough that you just plug into your computer, use the formula, but the answer should make sense, right? It should go in and it's, oh my gosh, it's negative. Do you think this is right? It's negative. But you know that freezing point is 0. 0 degrees Celsius is 32 Fahrenheit. You live in a temperate country. 32 F is freezing point. So then this is smaller than 32. Yes, my answer is correct. Even if it's negative, it makes sense. Okay? Okay. Okay, so this is another example here. We did quantitative versus qualitative. We did measurements, so we did quantitative first. Qualitative is what? The one that we said, descriptive. How do you describe it? Both are important because it helps paint the picture of what you're observing. Plus, if you write it down, then another person who's doing the same experiments will have an idea, not just by the numbers, but how the appearance is of what is going on. So that is why quantitative versus qualitative measurements are important. And always we have to write down whatever we see or observe during experiments. That's important. Later on, especially when you're asked by your supervisor what's going on, you have your lab notebook, your log book to show that this is what happened. Okay, in addition to quantitative data, writing numbers big and small, we also have writing numbers and looking at how the measured data, the numerical value is what? The precision and the accuracy of the measured value. What does that mean? Precision and accuracy. Are those two terms? Do they have the same meaning? Accurate and precision. Do they have the same meaning? Quantitative data. Accurate versus precise. Are they the same words? No. What is the difference between the two? Anyone has an illustration or an idea? Anyone? Who wants to, let's go look at sample data before going to okay, here, let's go to this. Are you seeing the tables?
Yes.
Okay, so 3 students, X, Y, and Z, are assigned the task of determining the mass of a sample of iron. Each student makes 3 determinations with a balance. A balance is a scale. The results in grams are for student X, 61.5, 61.6, 61.4, student Y, 62.8, 62.2, 62.7, student Z, 61.9, 62.2, 62.1. And then what they did here is they got the average. Okay, so they added the 3, 1, 2, 3 divided by 3. Student X got an average of 61.5. Student Y got an average of 62.566. Student Z got an average of 62.06. The range, meaning the difference of the biggest value minus the smallest value, is for student X, the range is 0.2. So that's 61.6 minus 61.4. Are you following? Yes? You're looking at the
Yes.
data, you're following. Student Y, the range is 0.6. Student Z, the range is 0.3. Now, the actual mass of iron is 62 grams. Okay, so that is your standard. The iron weighs 62 grams. Which student is least precise? Which student is most accurate? What do you think are the meaning of precise and accurate? Are they the same words? You said it's no. So then, based on this, do you think you have an idea which of these students is the least precise, which is most accurate? What do you think? Why is least precise? Okay, why Mohammed? Why do you think? How did you base your answer? The range. Very good. So what does that say then about precision? If you based it on the range, what do you how does it say about precision then? It would mean what? What do you think? Okay, where is my participants raising their hand? Lauren, raised your hand.
So, yeah, so why would be least precise? Because it's not exactly 62 grams, right?
Okay,
And then, because I just feel like precise would be more as like an exact, and accurate would be like just something that's close to it, like closest to the actual value would be
close
precise.
to the actual value. Very good. So close to the actual value, that is accuracy. So closest to the actual value, which is 62 grams, would be what? Which would be the most accurate then, based on Lauren's definition of accuracy and precision? Which would be the most accurate measurements? You says, what do you look for? Which is closest to the actual value? The actual value is 62 grams. Which is closer? 61.5, 62.566, 62.06. What is the difference here between 61.5 to 62? Is 0.5. What about the second one? 62.566 versus 62. 0.566. What about letter Z? 62.06 versus 62.06. So which set of measurements is closest to the actual value? So it's student Z. Hajar said student Z. That is the correct answer. Is everyone following? Accurate if your measurements are closest to the standard. Okay. Precision. What is precision? Did Lauren say something about precision? I forgot. Precision.
I said that it's like the exact like amount. It's like, yeah, accuracy is like how close it is, and like precision is like what it is, the exact amount.
Okay.
Correct. I don't know.
So precision, it's also the data are just close to each other, but it doesn't mean that it agrees with the standard. Do you follow? So if the data is precise, it means the data are close to each other. They're precise. So how do you figure out if the data are close to each other? You look at the biggest value and the smallest value. Based on this, which one are the numbers all over the place? You have a very big difference in the values. That is a question here, least precise. X, Y, or Z? Brianna says Y. That is correct. Y. Who wants to say Y?
Oh, see, I thought you were saying the letter Y.
That student Y is the correct answer, and student Y.
He has the biggest range, or that person has the biggest range, meaning that
That is the one with the biggest range. Very good.
Yeah.
So that means the numbers are far apart from each other. Are you following? Okay, least precise. Which of these data is the most precise?
X.
X, okay? So, okay, and most accurate is student C. So to summarize, this is a picture of what we talked about. Precision refers to the closeness of measured values to one another. A is precise, correct? C is precise, right? Accuracy. Accuracy refers to how close a number is to an accepted standard value. So B is a little accurate because it's going around the bull's eye, but C is the most accurate and D is like all over the place. C, yes, Kyle, that's true. C is both accurate and precise. Do you follow?
Yes.
Maybe D had, if we talk more about errors, maybe D, the wind was all over the place. He couldn't find a bullseye. Or maybe his stance was wrong. Maybe A, what happens to A then? Why did it all go here? They're precise. What happened to the guy who did A? A has an eye problem, maybe, so he needs to calibrate his eyes, or maybe his stance was wrong. So it all went to here instead of the bullseye. Okay?
Nah, the guy moving the target was just being spiteful.
You don't want to be the one behind the target.
Being spiteful.
Okay, so that is the difference between accuracy and precision. Okay, so this is measured numbers. We did that. And the last topic is density, and we're off for today. So density. Oh, and then I'm going to show you on Blackboard where you can get for the quiz for next week at 10 a.m. Like I said, 10 a.m. I'll make it available to students. And it goes from 10 to 10:10. Make sure you are on Blackboard. Turn on Zoom first, turn on Blackboard, and then you can private chat me if you have a question on the quiz on Blackboard. And we're meeting not next week because next week is a holiday. We're meeting September 10th. Look at the CUNY calendar for the holiday. I think September 3 is the only holiday we have. All the Fridays after that, we're meeting. Okay. One quiz at the beginning. I'm going to do polls during the class. And I look at your how you do with the quizzes, and I might have in the middle of the lecture, like a pop quiz. So, okay, back to density before we sign off. The David Letterman show. What is a quantitative data? Who wants to answer, Michael? We did this, quantitative versus qualitative.
Isn't it like data, but like it's based on observations?
Okay, where quantitative is where you can measure something. You can actually have, quantitative is when you have numerical values, an actual number to write it. versus qualitative, something that you perceive. So a color, or you can say hot or cold. But when you actually have the numbers of a cold, what is the difference? And that would be quantitative. Okay. Okay, so Kyle has a good something to think about. Quantity, N, number, quali, L, quali, and that's the root. Okay. Qualitative is colors. It feels hot, but if you put a number, that's how you feel it based on observation. So Michael, does that help? Okay. So I went back to David Letterman. He had a segment. He said, "Will it float?" And then they'll put a thing in a bucket with water, and whatever floats and whatever sinks, they make a guess out of it. So here, density is what? You see it float or sink, but actually it can be converted to a quantitative data because you have numbers here, densities. And densities are used to what? To look at a purity of an object or purity of your jewelry, for example. Each metal has its own density. And that someone would tell you that this is pure gold. And then they look at the density of your jewelry and it's not pure gold. It has other metals mixed into it. So, which is the most dense object here in the picture? Lead. Lead is, okay, we talked about units. What do you think the units are for density? Grams per volume. Very good. The per means it's over. Okay, sometimes the slash, you see it. That means when you do a mathematical operation, you have to divide it. Okay, it's not on the same side of the fraction bar. That is important because when you do dimensional analysis, there has been so many mistakes on that. Okay, it's mass over volume. So that's the formula for density. So cork is 0.26 grams per ml. Ice is 0.92 grams per ml. Water is 1 gram per ml. Aluminum is 2.7 grams per ml. Lead is 11.3 grams per ml. So density you can measure. If you have a scale, then you can put it on a balance. And if it has a regular, it's a regular object, regularly shaped object. So if it's a cube, length times width times height. If it's a cone, what would be the volume of a cone? Who remembers the volume of a cone? What's a measurement of a cone? You remember? Pi r squared h.
Yeah, pi r squared h.
Okay, so you can measure. What about if it's an object where
Now, pi r squared h is a cylinder, if I'm correct.
a what? It's a perimeter?
No, it's a cylinder. Pi r
Oh,
squared
it's a
is
cylinder.
I think there's a fraction with the cone. That's 1/3, I believe. It's 1/3 pi r squared h, if I remember.
Okay, we can look into that. But what I'm saying is if the dimensions are regular for an object, is there a raised hand here or no? Brian, you raised your hand? Or that was from before? Oh,
Those are from way, way back.
Lauren has a hand up to. Ryan, R-A-Y-N, you just raised your hand, right? Oh, you okay. Okay. What was I saying? Oh, what if the object does not have a regular shape? Then you cannot measure its length times width times height or its radius.
Integration.
Then what do? How do you figure out the volume of an object?
Calculus.
Okay, what do you calculate?
Nah, I just know that you use like calculus for stuff that have like irregular shapes.
Okay, what is a simple way to do it?
I don't know. You just fill it up with familiar shapes, I guess, until you get all the area.
Who wants to see how much volume an object, volume of a cone? Thank you. So who was it who was saying the pi r squared h over 3? Very good. It's a volume of a cone. But anyway, back to objects where you don't have a regular shape. How do you figure out the volume? Anyone? Do you know Archimedes?
Oh,
What
yeah. I heard of his name.
famous yell? I guess you don't know Archimedes. He is why you have these ships that are made of steel float in the oceans. Based on what? What do you do for irregularly shaped objects? How do you get the volume of irregularly shaped objects? You do it by?
Water displacement.
Very good. Water displacement. So what does it mean? Who made the, how come I don't know who's yelling out? Where do I see the person?
That was Kyle.
Okay.
Oh,
Okay.
is it like you just
How
fill
do
up?
you do water displacement? Yeah?
It was Kyle, but my
one
guess is
who-
you just fill it up with water, I guess, right?
So you fill something with water, you know the original volume, you put the object in, and then you see how much the water moved up. Whatever the moving up means, that's how much the object that you put in went down. Okay, so that is what you do when
I haven't heard about that in a long time.
okay, or if it's a salt cube that dissolves in water, what do? You put something that salt doesn't dissolve in, so you put in oil as long as you see something displaced. Okay, so here you have your zinc, you put it in the water, you want it blue because you can see it better, and then you put it in a graduated cylinder. The original volume is 35.5. When you put your cylinder of zinc, it went up to 45. So how much does zinc, what is the volume of zinc? It's 45 minus 35.5. So density is mass over volume, 68.6 divided by 9.5. What is the 4.5? Marbelli, 4.5 is what? 45 minus 35.5. Oh, it's 9.5. 45 minus 35.5. And you're told from the scale that the mass of your zinc is 68.6 divided by 9.5. So the density of zinc is 7.2. And then you'll know if it's actually zinc, because you can check. What is the density of zinc? Is it here? Well, it's not here. It should be here. Well, it's not. But these are the densities. And densities are the same at a specific temperature. So they always put in a temperature here, because as we learn later on in gases, the volume changes when you go from solid to liquid to gas, okay? Because it depends on how fast your atoms move. It takes up the volume in solid and liquid and in gas at each temperature. So you're always told what the temperature is, and the density for that object is consistent at that temperature. Because an example is water. Water at 4 degrees is 1. When water turns to ice, it's gonna go to what? Ice is 0.92. Water especially, you could have the whole semester in food technology, in post-harvest production, probably in medicine, because water is a special molecule. So only in water, well, maybe not only, but that is one that you can think on top of your head, where water, as it turns to solid, it becomes less dense, okay? From liquid water to solid water, it becomes less dense and it floats on top. And that's why animals can survive the winter. And with that, okay, with that, this is our last slide. And then here, density of a metal. Okay, like I said, this is your displacement. So 48 grams of metal, if the level of water in a graduated cylinder rises from 25 to 33. So here, how much volume does the metal occupy? Yes, we will get this on the what chart? Oh yeah, if I ask you the ID of a substance, then you will have a chart. Yes, Mohammed. What was it? What was, okay. Well, what does that mean? This is just a formula. You can see mass over volume. So what is the mass? 48. What is the volume of the metal? 33 minus 25. So what is the density of this metal? So 8 grams per cc. And can we identify this metal from the chart? Here. Do we have an 8 grams? Okay, so it might be, what would it be more, iron or copper? Based on the value you have, it would be more iron. Maybe it has an impurity. So that's how you use density. And that is our first lecture. And it is gonna rust in water. That's why they're doing graphene now to put in bikes or other stuff, you know, those alloys. Go to Blackboard, please. And I am gonna make available, just so you know how to get to the Blackboard site. Okay, let me, can you come up, open up your Blackboard right now? I'm on student, wait. So I will give you exit. So you will know where to go. It's going to be in course materials, quiz, and there's a quiz folder. Are you on Blackboard? Just so you have just so you'll know where to look for it. And then it's going to be August 27, make available. Okay, the August 27 one, it should be, there should be a quiz there. That should be available. And then you can use that as practice. And then it should submit in 10 minutes. And that is where you will find our quizzes at 10 every Friday. So I will stay and you can take the quiz. And if you have questions, I'll be here on Zoom. Okay, so just try out the quiz. Everyone sees it on Blackboard, know where to find it in Blackboard, the quiz for August 27th.
I'm sorry, where was it on Blackboard? Could you repeat that one more time?
It's on course materials. Oh, wait, here. You go to Blackboard, course materials, do you see? It's on,
Yeah, I see quiz. Yeah, on August 27th.
yeah.
Right.
That's the practice quiz. It's not graded. It's for practice for you, so you'll know where to find it. But look at it and answer it and see how you take it and make sure it's submitted and all that. Okay. And if you have questions, private, chat me on here. My Zoom will be on 10 minutes before class, before 10. And then I'll stay after in case you have questions. And like I said, make sure your Blackboard's working because I'm going to be posting homework and quizzes, exams on Blackboard. So make sure you access Blackboard. So take the quiz and have a great weekend and see you in 2 weeks. We'll meet September 10 for our first quiz at 10. Let's see if you're taking the quiz.
Thank you. Have a good day.
You too. Have a good day.